Okay, the purpose of this chapter is to talk about the linear design models. And the concepts that we are going to cover in this is something very interesting. Is how do we use linear techniques to control complex nonlinear models? And let me tell you, if you talk to someone who is trained in nonlinear dynamics or controls, such as myself, they will say, no, linear technique will not work for nonlinear problems. That is true, except about 70 to 80% of the times, if you design your linear control properly, it will work for the nonlinear system around that operating regions. And you will see, if you decide to go work for Bell helicopters, or for that matter, Boeing, you will notice that majority of their controller algorithms are one or the other form of linear control. Why? Because they can be validated for the entire duration of operation. Nonlinear control, nonlinear function, you can have division by zero, or floating point arithmetic, or the processor may choke, or two processes may collide. So FAA has strict regulations on the flight control systems and how they can be validated. I'm not saying nonlinear techniques cannot be used, but validating them for an actual flight is difficult. Not impossible, but difficult. So for typical operating regions that we encounter for civilian, and as a matter of fact, cargo aircrafts, you can resort to linear control. And in this lesson, I'm going to tell you some important tricks how to achieve that in practice. And understanding this is very important, because when we are going to program the Mambo, most of the controllers that we will try on the Mambo or any flight vehicle will be linear. So these are the equations of motion that we talked about. These equations look complex, and depending upon the flight vehicle that you are analyzing or designing or controlling, they would become more complicated. But the first line of analysis is ignore the nonlinear terms that are contributing to very small dynamics. Then understand the operating regions. For an example, if the aircraft is in level flight, or aircraft is climbing steadily, or quadcopter is hovering, then find out the trimming conditions. Trimming is a dynamic equilibrium wherein some of the velocities are set to zero, or some of the state derivatives are set to zero. Not all of them, some. Because please try to understand, if we set all the derivatives to zero, that means the aircraft is static. So it's no longer an aircraft. If we set up the parameters that are not relevant to the flight envelope at zero, we are constraining the system more than it is needed. So finding a solution will be tricky. So the thing here is identify the states that absolutely have to be zero, and identify the states where there has to be an absolute constraint. So once you do that, these equations become super complex. And once you start coding it, you will realize that they actually include the effect of control surfaces. So depending upon the exotic control surfaces that you are going to have different terms. Typical flight envelope that we are looking at is a simple coordinated turn with wind. We are looking at the stability condition for the coordinated turn, so that the aircraft can bank. That is another. So whenever someone says aircraft is banking is not just yaw. Banking is a coordinated turn. So you will see that in aerodynamics literature, the aircraft is banking. So that is a coordinated turn. And if you use something like an IMU or airspeed sensor, then that is a special flight condition when you have to compensate for the apparent effect measured by the flight control or the IMU. Because please try to understand, when the aircraft is banking, you will notice that in addition to its forward acceleration, it's extending or it's experiencing the lateral acceleration, which means if you were to use the accelerometer, just like the spirit level in your smartphone, you would get a wrong measurement, because right now the acceleration that it is measuring, it is not related to the true component of gravity. There is a centripetal acceleration component used in it. So what you need to do is, at that time you need to decouple, and then you have to use some algorithms, like look at the coupling and then approximate it, and then just rely on the gyro data. Just don't use accelerometer and so on. So remember this: if you get into flight control, whenever you are banking, you cannot trust the instrumentation or the IMU or accelerometers and gyros. So we talked about the steady state, effect of steady state. Then we talked about calculating trim, and the reason the trimming calculation is important, because we need to know the operating point before we linearize. So because that linearization is valid where the aircraft is trimmed. So if the aircraft is trimmed at some other point, then your linear model is going to be valid there. If the aircraft is trimmed at some other operating point, then your linearization, whatever we are doing, even the autopilots, whatever we'll be doing in next class, will be valid in that region. So if for some reason, if that region changes, then your model will not work. So we talked about what it entails when we calculate trim. And one thing I want to tell you is, calculation of trim is not an easy process. You will have to solve optimization problem. But the good news is MATLAB provides the tool for finding the trimming condition. So you can actually use the trimming function inside the MATLAB, and MATLAB would find the steady state and trim. Depending upon what algorithm you use, it may give you solution quickly, it may not give you solution quickly. But that is something you can understand by trial and error, looking at the initial conditions, final conditions, operating conditions, etc. So once you start playing with trimming an aircraft, you will notice that you will have to be very careful about the choice of the solver, optimization solver, because it's done numerically to get the solution. Sometimes you will get multiple solutions. Then just like our inverse kinematics approach in robotics 1, we have to use the appropriate trimming conditions. Now, as you can see, this is the general idea. We are going to set all the derivatives equal to, sum of the derivatives equal to 0. The derivative on h dot, which is the velocity in the upward direction, which will be set as VA sine gamma, which is the component of airspeed in the downward direction, and psi dot, which is actually yaw rate, that is decided based on the coordinated turn. And Pn dot and Pe dot, the forward velocity and lateral velocity, we are not worried about. So whatever values we get, that's totally fine. So what may happen is, and please try to understand, when someone says that aircraft is in level flight, that does not mean that aircraft is flying in a straight line. Aircraft do not fly in a straight line. Aircraft do not fly horizontal. Typically, when you have an aircraft, you're going to have some type of side slip, and the aircraft is going to be something like this. And the pilot would do a periodic course correction to bring the aircraft back to the trajectory it needs to be. You will never have an aircraft flying straight. It's not a rocket. Rockets don't fly straight. So then the way we solve the trimming problem is by means of constrained optimization. In the last class, I gave you a basic what optimization is. At the core, optimization is taking the first derivative, equating it to 0. And depending upon if you constrain the value of states, then you get something like a constrained optimization. Or if you add some additional condition on the derivative or the states, that is constraint optimization. If there is no boundary, no constraint, then that is unconstrained optimization. And if you are in linear algebra, or as a matter of fact, if you study machine learning, usually we use a gradient descent algorithm to find the optimal. Please understand, there is a global minima and there is a local minima. Local minima is in the vicinity of the operating point. Global minima is the minimum all across the domain. For trimming, we are interested in local minima because there might be some other better solution, but if it is not close to where we are operating, it has no use for us. So we are looking for a local minima. Typically, we will have some constraints, and I want to tell you that this is the mathematical way of writing a constraint, where you will add some limits on various functions. There will be equality constraints, there will be inequality constraints, and at the end, your solver should give you the solution that satisfies all these conditions. And that is the reason why we want to have as many as less conditions as we can, because if we make it too constrained, then it won't give you a solution. So just be careful with that. And if you have taken Professor Zhang's optimization and controls, probably you must have studied these techniques and methods in a lot more detail. Yeah.
How many times in a second do we calculate them?
So usually what happens is, just like Runge-Kutta integration, there will be a tolerance that you can set. So numerical algorithm will continue to refine, just like gradient descent or weighing functions in neural networks. So basically it will continue to do it till that threshold is met. And that depends upon actually how accurate you want your system to be. So this is generally, so once you start working on the project for this chapter, you will get better understanding of how to do the trimming, what trimming means, and then how we can translate what we are saying in terms of equation, and then translate that to the actual simulation or flight. So you can have combination of equality, inequality constraints. And again, this is just a mathematical representation of what that means. Now, next part, which I want to talk about, and I want you to understand this approach very, very carefully, because this is the way majority of the practical controls are done. It's great to use nonlinear control techniques all the way to Lyapunov technique, or you can do exotic control techniques that controls engineers love to propose. But when we try to implement, always start with the simplest technique that you have confidence and that can be validated and that can be implemented. If thing cannot be implemented on a real embedded system hardware, most likely it will not be used in any real application. So what I want you to understand is, we have this lateral transfer function. First and foremost, equation is nonlinear. Transfer function does not exist for a nonlinear system or nonlinear dynamics. Remember this. Equations that we are dealing with are nonlinear. They are coupled. So in a true sense, the transfer function does not work. So what are we going to do? First, we are going to look at that nonlinear function, then approximate it to the best of our judgment. And after approximation, the things that we cannot cancel, we are going to treat them as disturbance. Now, what does that mean? It means, imagine if you have an equation, mx double dot plus kx plus k2x cubed is equal to f of t. This is actually called, I think, Duffing's equation, and you will see books and books on analysis, control of Duffing's equation. And there are various variations of these. However, a simplest way that this whole system can be controlled, okay, and you will appreciate this. So what I want to do is, I want to control this system. So basically I have a spring mass system where the spring is nonlinear. And I want you to understand this, the very basics. So I have a spring that is something like kx plus kx cube. And there is an external control input, say f of t. What I want to do is, I want to control the motion so that this is asymptotically stable. So let's think about the case. I want to control the system so that mass is asymptotically stable. What is the practical application? Imagine you have a suspension with zero damping. So basically it's a mass and spring. Yeah.
What is the meaning of asymptotically stable?
Asymptotically stable, eigenvalue real part less than 0. Motion decays after some time. So eigenvalues real part less than 0. Eigenvalues are on the left hand side plane, not on the imaginary axis. Everyone okay with asymptotic stability? So think about that ball rolling in a bowl. Okay. Now let's understand, and believe it or not, this is how the Mercedes suspensions are tuned adaptively. So now understand that I have this model and I want to make it asymptotically stable. So what I'm going to do is, this is very interesting. I'm going to add an extension and I'm going to add an electromagnet. And wherein what I would do is, I would vary the strength of the electromagnet, so that the plate that I have in the center exhibits the behavior I want that mass to exhibit. Everyone understood this? So think about it like it's a handle. And what you are going to do is, if you will adjust the electromagnets, the strength of the electromagnet, so that you will sort of control the motion of the centerpiece. And that strength of the electromagnet can be very easily varied using the amplitude of the current and the frequency. So you can simply use a PWM to control the intensity of the magnetic field. So it will be just a simple PWM controller. And Arduino can do that. Now what you want is, you want to program the Arduino, the sketch, to implement a controller algorithm. So let's try to understand what I'm going to do. Imagine what I want to do is, I want this system to be simply stable, not asymptotically stable, simply stable. Give it an input, it continues to oscillate. Then what I would do is, I will use the electromagnetic force, which is f of t, is equal to k2 x cube. And what I would do is, I would somehow measure the displacement of this guy using an accelerometer or maybe some type of a displacement pickup. So what I would do is, I would measure the displacement of this mass using some type of a pickup, or as a matter of fact, the disturbance in the electromagnet can be used to measure the displacement or relative displacement. And then I provide the feedback k2 x cube. So as soon as I substitute k2 x cube feedback, what has happened, that my dynamical equation of motion is now converted to mx double dot plus kx is equal to 0. Everyone understood this? So if I input a feedback or the electromagnetic force as k2 x cube, k2 is a constant, x cube is the magnitude of the displacement. I would measure the displacement every time in milliseconds at millisecond sample. Feed that electromagnet, then what will happen is, that dynamical system would get converted into mx double dot plus kx is equal to 0. That is a simple spring mass system. You pull the mass, it will continue to vibrate. Everyone understood this? So which means the nonlinearity is cancelled using a nonlinear feedback. Everyone understood this? Now, some of you may ask me, now what? Understand the resulting equation now you have after the nonlinear feedback is linear. Then you can use any linear technique to control it, such as the transfer function. That is the key. And in certain cases, if you have some residual effect that you cannot cancel out, you would add some additional controller input, or you will give it some additional controller input. So you will make electromagnet stronger than what it says it should be, to compensate or to dissipate the effect of disturbance. Everyone understood this? I repeat this once again because this may look simple, but unfortunately, the people who don't have experience with building actual control systems, flight critical control systems or critical control systems, they will not tell you this. So remember this. If you have a robot, okay, which has differential equations you derive, you find those equations are nonlinear, and you want to design your own controller, nobody is gonna make a custom controller for you. So you have to select an appropriate controller that is available in the market. What you can do is you can tune that controller to behave as per your requirements. What does that mean? It means you can adjust the feedback of the controller, or you can vary the strength of the control depending based on a linear control law or a non-linear control law or a combination of linear and non-linear control law. And that is how things work in practice. I mean, I have seen folks using Lyapunov based techniques, global controller. But if you want to design a global controller, most likely the equation that you want to come up with for the control law will be super complex. And you may not be able to prove that control algorithm will work in real time, because at the end that control algorithm needs to be implemented on a microcontroller. Microcontroller has limited floating point arithmetic capability. It, depending upon the microcontroller you use, you may or may not get the frame matching, which means the control law will come after the state has crossed. So remember this. Okay, the next thing which I want to talk about is, since we understand the basic logic, we have this equation which is phi dot. And why we want phi dot is because we are doing lateral control. So we want to control the lateral states. What are the lateral states? I need to bring my 3D printed airplane. What are the lateral states? Lateral states are roll and the motion in the lateral direction and yaw. So what I'm going to do is I'm going to look at how do I control the roll motion of the aircraft, yaw motion of the aircraft, and sideways motion of the aircraft. And the best way to do that is start first with the roll rate equation. Phi is roll rate, how fast aircraft is rolling. This is dependent on P. Can someone tell me what P is? P is the actual angular velocity of the aircraft about x-axis. And then you have roll and yaw coupling. So basically you get Q sine phi tan theta. Remember, theta is this. And then you have phi is nothing but this. And cosine phi tan theta. Now here, assuming, and this is something you need to keep in mind, assuming the angles are small, say, so we are looking at lateral motion. So I can reasonably assume that my theta values are small. When my theta values are small, I can just say my tan theta is small, and then those two terms vanish. I can also make an assumption that my roll angle is small. But when you say small, that means it needs to be less than 17 degrees. So pitch of 17 degrees is possible, but 17 degrees roll is difficult. So basically, you can have an aircraft pitching less than 17 degrees, like 8, 10, 12, but rolling, I have seen aircrafts roll more than 17 degrees. So what that means is, even with that assumption, I'm gonna have some residual error term, which is given as dP1. Everyone understood this? So what has happened is I'm treating this term, and please note, this is the nonlinear term. And this nonlinear term is treated as this guy. So what I have done is, I have this nonlinear term, I equated that to a variable, but please note that variable is linear. Are you with me so far? I'm not saying it is dphi1 square. I'm not saying it is dphi1 cube. I'm just saying whatever that nonlinear function is, it is dphi1. Everyone understood this? And I'm going to design a controller algorithm so that that dphi term becomes 0. Next part is, I need to differentiate. So I differentiate. And why do I need to differentiate? Because, all right, and this is something that you will learn. Imagine P we have in the original equation, but P itself depends on something, right? And remember, the equation for P dot is one of the 12 equations. Remember that? So what I'm gonna do is, I'm gonna differentiate this. As soon as I differentiate, I get an equation for P dot, and out of those 12 equations, I will grab that equation for P dot and substitute it over here. Everyone understood this? May seem convoluted, but this is a standard technique. And then clearly you get this very horrible looking equation. Same trick. Identify what nonlinear part exists. Now clearly at this point, what's going to happen is, watch. We started with dp1, right? Initially, we took the derivative. So can you see that dp1 dot is popping up in my phi double dot equation? Are you with me so far? When I substitute the terms for P dot, I get some terms which are pseudo-linear, and I get some terms which are super complex and non-linear. Do you agree with me? All that big term, I'm replacing this as dp2. dp2 consists of dp1 dot and the nonlinear terms that came into existence after substituting value for P dot. Everyone understood this? Same thing. Grab those terms together and call it a linear term. Everyone understood this? Now, you can look at this equation and say, wow, this equation is linear, which means I can take a transfer function. Problem solved. Do you remember what a transfer function is? Ratio of output divided by input in a Laplace transform. And for transfer function, you should remember, if you have x dot, it becomes sx. If you have xt, it becomes xs. If you have x double dot, it becomes s square x of s. Right? So now what you need to do is, you need to see what is an output, what is the input, take transfer function, and trust me, your life has just become a lot more easier. So that exactly is what needs to happen. Take this equation, take the derivative, substitute this in here and then simplify so that at the end, the final equation, what you get is linear. Are you with me so far? And this technique you will see being used in robotics a lot, really a lot. Because imagine if you want to implement a very highly complex nonlinear control, you're gonna need very expensive microcontroller. It needs to perform a lot more floating point arithmetic, which means at every arithmetic, it's gonna consume a lot more power. There is a lot more possibility of process slowing down, frame not matching, etc., etc. You will see that when you program Mambo. You will notice that even though your controller algorithm works well, but initial condition 0, even the initial condition is 0. No, we are in dynamic equilibrium. Initial conditions, if the initial conditions were 0, if all of the initial conditions were 0, that means the aircraft initially was at rest. So no, we are trimming, which means aircraft is flying. Everyone understood this? We are talking about dynamic equilibrium. Okay, enlightenment. So now, what I want to tell you is, I want you to see that we had a super complex equation. Remember, we tried to convert it into linear, not happen. Try to convert it into linear. Finally, we got an equation that we can find the Laplace transform of. And I will show this just for one case. Everyone comfortable with Laplace transform? The only thing that you should remember, time variable converted into S variable, x dot, sx, x double dot becomes s square x. So what that means is if I have this something like this will become s square phi of s is equal to minus a phi. Phi dot will become s phi of s plus again a2 phi 2, then delta a becomes delta a s, and the last term, remember, which was the combination of all the non-linear linear terms, that crazy term will become d phi 2 s. Are you with me so far? So now you can take phi of s on one side, and then you have a nice transfer function that you can analyze. Everyone understood this? Okay, so I will answer your question with an example. So bear with me for a second. So I need to show you the MATLAB's example to show you the effect of initial conditions on the Laplace transform. I can try to answer that question, but it would be very theoretical. So for an example, even if you take Laplace transform, if you want to find out the time domain solution, you need to substitute the initial condition. If the Laplace transform is in general for a transfer function or for any differential equation, depending upon the stability characteristics of that system, the effect of initial condition will be diminished as the system goes through the stable equilibrium and onward. I need to show it to you with MATLAB code so that you understand what these gibberish words mean. But that is what it is. And I'm sure the person who asked me the question has understood it. So I will move on. So I just kidding. So what I need, so now what I want you to understand is this is extremely important, and you will use it again and again. This guy is this guy. Do you agree with me? That is a disturbance. That disturbance is acting on its own transfer function. Do you agree with me? And gets fed to something here. Do you agree with me? This is the aileron input. This is given by pilot. Which means what I need to do is, at the end, to control phi, I need to provide sufficient aileron input that can compensate the effect of disturbance and actuate the system so that I get desired peak. I will repeat this once again. Once you go to industry, you will realize how powerful this technique is. What I did, I took all the nonlinear, unmodeled dynamics and treated it as a disturbance. Whether that disturbance is linear, non-linear, maybe quasi or stochastic, doesn't matter. It's a disturbance. I don't want it. So what I did, I found out the transfer function that is acting on the disturbance. So I found out the transfer function which is acting on the disturbance, which means, and then I see that this disturbance gets fed to the actual linear transfer function I'm interested in. You agree with me? So imagine if the disturbance would have been zero. Imagine if disturbance would have been zero. You agree with me? I would need some input delta A that will get me the desired output. Agreed? But since there is some disturbance, what it means is I need to give more input to cancel the disturbance and control the dynamics. Everyone understood this? This is exactly what I showed you in the last slide, where you have minus kx square as an external input, and then basically you take care of the disturbance, system becomes linear, and you control it with PID. Everyone understood this? Same thing is going to come at us again and again when even we design autopilots. Even if you want to come up with a path planning algorithm, you will do the exact same thing. Okay, so it's so important that I want to pause here and answer any questions before I begin the next part. This is how the robotic systems, automation systems are controlled in practice and applications. Okay, now next is the course. What is the meaning of course? Course is basically, if you think about it, course angle is the difference. So you have to find out what is the course angle, which is chi dot, which is given as G divided by VG. And if you don't remember what VG is ground speed. VG is ground speed. Is equal to VA plus VW, where VA is the airspeed, VW is the wind speed. Everyone understood this? So now here is another trick that is used a lot. And keep this trick in mind when if you take a nonlinear controls class, people will give you all type of argument that this will not work. But somebody who is working in industry and done actual control system and flew aircrafts with that control system will tell you this works. Okay, now here to start with, we have the exact same problem. That G is a constant, VG is a parameter, which is a linear parameter, but tan phi, tan phi is non-linear. You agree with me? I am not going to consider tan phi is equal to phi because I can't guarantee that my roll angle is going to be less than 70 degrees, which means I cannot get rid of that non-linearity. Many a times you can't, because in your practical flight envelope, the aircraft will bank or aircraft will roll more than 17 degrees, which means you have to take that into account. So then the question is, what next? Next question is, you subtract. Finally, what is our goal? This complicated nonlinear equation should somehow be converted to linear equation Somehow we have to find the transfer function and we should be able to implement in our control system. And then the actuators should move so that that control surface can deflect. Everyone understood this? At the end, what's going to happen? Those hydraulic actuators of the aircraft will deflect the control surface depending upon the aileron input. And then basically the aircraft dynamical equations of motion will be modified and aircraft will behave the way we want. Here is the problem. This tan phi, somebody will say, oh, why not I treat that tan phi as phi? That's fine. The only problem is the roll angle will not be less than 17 degrees, which means your model is not going to be accurate. The model is not accurate. Best thing, let it be as is, and then I will add and subtract. Remember, adding and subtracting the term which is linear that I can control. So now what I have done is, check this out. G over Vg phi. Everyone agrees that this is a linear term. The original equation does not have a linear term. And the linearization is not valid. Now what? So I went, and actually this actually happened here. So I went to a public speaking class and the speaker said, oh, you need to speak as if you are trying to impress the person who is sitting in front of you. Okay. So then someone asked, like, hey, what if I don't find the person in front of you attractive, or or something like I don't have a person whom I want to impress. But then he said, then imagine a person in front of you and then try to impress. Okay, so you go extra mile. Anyway, that's what is happening. We are subtracting and adding. So once we do that, what happens is you get this term, which is because of the additional spurious term that we added. Can you see that? This is where we add, this is where we subtract. At the end, effect is the same. But now what has happened is we got a linear term and we got this disturbance. Are you with me so far? Again, same thing. Take that disturbance, call it another linear term. Take that disturbance, call it another linear term. And then take all this and feed it to your original equation. So basically, as you can see, that up to this part, comes from the equation that we have derived here. Now the next part is we are controlling the course. So you have this stuff. So this is the disturbance. But the good news here is that disturbance does not have a transfer function. So just feed the disturbance. So can you see up to this part was the control or the transfer function that we designed earlier. Here the disturbance comes in, and then here you have a transfer function that acts on everything. Everyone understood this? What does that mean? Which means our aileron input need to be, earlier it was a little bit strong. Now it needs to be stronger so that we compensate for the disturbance here, control the dynamics, compensate for the disturbance here, control the dynamics, and get the desired course. Are you with me so far? Then next thing is, yeah, it becomes more, little bit more complex. But at the end, that is the trick. Now we are looking at the lateral transfer function side slip. So imagine side slip means the aircraft is slipping. So aircraft has some side slip angle. Can someone tell me where does side slip appear in our frames of reference? Remember we talked about all those things. stability frame to wind frame. That is where the side slip occurs. So if you have a no wind condition, you get VA sine beta. If you have a constant airspeed, you get V dot. You can basically say, okay. So if there is no wind condition, then you have V is equal to VA sine beta. What I'm gonna do is I'm gonna use the same logic. I want to start with this dynamical equation, take the derivative, and as soon as I take the derivative, I have V dot is equal to VA cosine beta beta dot. Everyone understood this? In our long list of 12 equations, we have an equation for V dot, and we have an equation. Let me see. We have an equation basically that is replaced as V dot, and then some terms of that V dot equation, they are moved on to the right. I tell you the reason why. So these tricks are very practical tricks. So you have this no wind condition. Take the derivative. We got this. We have an expression from the 12 state equation. So we have an equation for V dot. Remember which equation is it? I don't remember the exact form, but at the end, this is the equation for V dot. And what I'm going to do is I'm going to substitute that equation in here. And then I'm going to collect the terms which are associated with beta or beta dot. So all the terms that involve beta and beta dot, they are going to be on the left hand side. Now some of you may ask me, why is it? This is because we want to control beta. So if you want to control beta, we need to take it on the left hand side. And everything else, so beta dot on the left hand side, everything else needs to be on the right hand side. And again, if you do the same mathematical jugglery, you are going to observe that you have this term, that is a disturbance. This term is beta, and this term is control. Are you with me so far? So the mathematical jugglery that I talked about, exactly the same thing happened. You combined all the terms. Then you had some nonlinear mumbo jumbo terms. You converted that. You say that that term is a linear term. And then you treat that as a disturbance. And you find out all these constant. So now understand this disturbance term is so complicated term that is arriving here. So this disturbance term is here. Everyone understood this? So what would my control effort do? Control effort would control the dynamics and cancel out the disturbance. So it becomes super simple at this point. Can you see that this disturbance term is coming here in the summing junction? This is the input that's get fed, and this rudder input. Now we are controlling the side slip. So if you are controlling the side slip, then basically you need to add the rudder. So rudder input is controlling the aircraft dynamics and overcoming the disturbance. Everyone understood this? And all of a sudden you have a very nice transfer function that you can run in real time. Next thing, we are going to go through the same process again for the longitudinal dynamics. Equation may look more complicated. Process is exactly the same. So what we are going to do is, you have, now let's talk about what control variables we have in the longitudinal. We have pitch. Then we have forward speed. So we will start with the pitch dynamics equation. So theta dot. Then, as you know, first step is to see if there is way to linearize this. And then I noticed that there is this nonlinear term that can be linearized. or that can be considered as one term. So all the nonlinear term is combined together. And some of you may say, why I didn't take into account the cosine phi. So I don't know if you noticed this, but here what is happening is we did an add and subtract type of combination. So we added add and subtract. So just to make sure that everything is consistent. So you combined the techniques that we talked about in last lateral dynamics in one equation. Then you differentiated. So you got theta double dot. Now you got this complicated looking equation. At the end, you just retained theta dot, theta, control surface, because elevator is the control surface, and everything else went here. Are you with me so far? And this equation, as you can see, is linear, which means linear equation, you can find transfer function. And you can actually find, so exactly you can treat these two equations together, and then you land up with this longitudinal transfer function. What is this longitudinal transfer function? This longitudinal transfer function will act, it will take the external disturbance. Please note, d theta 2 is an external disturbance with a very long expression. That disturbance will act on A2 theta 3, that term, that gets fed into the summing junction, and that disturbance will propagate and affect, it will affect the system dynamics. So your elevator input will compensate the external disturbance and compensate or control the system dynamics. But the story doesn't end there, because as you extend, you will realize that there is a d theta 1 that is coming in from the earlier part. So what you do is, now some of you may ask me, why is that I did not do this d theta before? Because you need to identify the correct summing junction, so that when you combine that block diagram, or when you combine, you get the original differential equations. Otherwise, this will be meaningless. You cannot just sum wherever you want. So it needs to be summed at an appropriate place, so that at the end, when you work out the equation, you get the result. Any questions here? And then what you do is, okay, to decide longitudinal transfer function, altitude from pitch, we take into account the h dot, which is the PD dot function, which is the rate of change of altitude, height. Go through the exact same jugglery. Can you see that there is VA, theta, all this stuff, and then that gets treated as a disturbance. Then you can find the appropriate transfer function, and then you can draw a block diagram representation. So this is a disturbance. This is a disturbance. And then finally, you have H. Everyone understood this? This is extremely important. Whenever you do it for the first time, it may seem that this is sort of convoluted, but once you work out the math yourself, you will become confident. So even if you have a nonlinear robotic system, even if you have any other UAV that you haven't solved before, which may have super complicated dynamics, we will take those dynamical equations of motion from aerospace engineers, and then we will control those equations the way we want. That is what a roboticist does. Okay. So robotics engineers are not domain knowledge experts. So nobody will expect you to devise or derive a differential equation for a super complicated exotic aircraft. That will be taken care by the engineers, the aerospace engineers, aeronautics folks. you will get a differential equation. And as a control engineer or as a roboticist, the control engineer can control it. But what you want to do is you want to control it, make it autonomous. So roboticist will, it doesn't matter what dynamical system it is. Once you understand these key fundamental principles, you'll be able to implement a practical control system. So remember this is extremely important, which is very, very useful. And you can use this technique to impress your interviewers. If you get a job, or if you get an opportunity to interview at robotics companies or aerospace companies where you are designing the flight control system. Everyone understood this? So I sometimes I get hardcore controls engineers saying, no, this system is not good. This system will not work. So if you work in nonlinear controls, which I do, my recommendation to you is, as a comparison, it's very simple to implement in MATLAB or anywhere. Just compare the performance of your nonlinear system with these types of linear transfer function techniques, or some simple approximation linear function techniques. Many a times, based on my experience, 70 to 75% times, the linear technique would work just fine. And that is easier to implement. So just try that. One classic example is, if you want to try the nonlinear or Lyapunov based technique to control an inverted pendulum, you can do that. Try a disturbance rejection linear control, that will also work. And implementing disturbance rejection linear control is computationally, well, depending upon the platform, may work faster. So in the update rate. Okay, so this is what we did. We combined these differential equation. Now the last part which I want to talk about is, imagine the concept of an airspeed. And what you have is, you have an airspeed VA, which is the vector sum of the aircraft velocities in the body. So U is the body X, V is the body Y, and W is the body Z. So you have a total airspeed, which is VA, which is the vector sum of all those velocities. Take the derivative. Take the derivative and try to simplify that with as many terms as you can. So if you take the derivative of it, and then if you substitute the equations, you are going to finally land up with an equation which is of the form something like this. Now there is a subtle point which is not discussed in detail, but that is present here. So what you want to do is, you want to somehow include the actuation variable into the dynamical equation. What does that mean? It means, if you were to look at the original equation, some of you may say, oh wow, this equation is VA dot. If I were to take the derivative, it is going to be a derivative of that complicated function, and as per UV rule, there will be a U dot, V dot, and W dot. You agree with me? Now understand, what I want to do is, I want to have actuation based on the angle of attack. So I am going to use some form of relationship that relates angle of attack alpha with the terms or the variables that are present in that equation. So there is one step in between. So once you take the derivative equation will not contain angle of attack, but you will identify the relationship that you can use to include angle of attack in that equation. And once that is done, and there's a very sound reason for that, because what we want to do is, we want to understand how that angle of attack influences the dynamics. So once you do that, believe it or not, there is this disturbance term And then what you do is you expand that dynamics, and then you get a complicated equation, something like this. And that once you follow through that substitution, at the end of the day, what you have is you have this equation. And this is a linear equation. For that, you can derive the transfer function, and all these complicated terms will be present. All these complicated terms will be present, but we will treat them as disturbances, or we'll treat them as a constant. Now, there is one more thing which I want to tell you. And my PhD was in nonlinear dynamics, specifically with time varying systems. So when I told my advisor that why don't we look at eigenvalue based stability criteria, he said, you're stupid, because eigenvalue criteria does not exist for time periodic system. That is absolutely correct. You need to find out the Fouquet multipliers and exponents. So there is a rich theory behind it. But here is what happens. Even if your system is time varying, if you start taking snapshots very fast in that frame, the system is a linear system. What that means is, if you were to take snapshot very fast, and then if your controller is able to implement the control algorithm as quickly, even though the system may be time varying, your linear control would work, and it works. So, I mean, nonlinear theory, my PhD was in it, so I know that Fouquet theory is the right way to do it. But when I talked to an aircraft engineer, I said, blade equations for the helicopter dynamics, they have time periodic coefficients. Why aren't we using Fouquet theory to why aren't we using Fouquet theory to find out the controller gains? He said, even though those equations are dynamic, the rate at which the variability is, we can actuate the controller at much faster speed, so that when in the window that we are looking, that system appears to be linear to us. And it works. Well, my advisor, he passed away. He would have never admitted that, because he never worked on the flight control system. So anyways, but nothing wrong in understanding theory. But remember when to apply theory, how to apply theory, what are the limitations, how you could enhance it, how you can make it simpler, how you can, so know the limitations as well. Okay, so now if you go on performing the same mathematical jugglery, which is nothing but high school math, you will realize that at the end, you're gonna get this equation, which leads to this block diagram representation. Everyone understood this? And I would let you work through this math, because it's super simple. The next part is, we did the transfer function. But since we are working in a linear domain, nobody prevented us from using state space models. So if you are from EE background, one of the required courses is linear system theory, right? Whatever we studied in linear system theory can now be used as soon as we deal with a linear map. And all the state space technique, all the LTR techniques, whatever you have studied, they can be added. I'm going to stop here, and I will talk about the state space approach and linear control theory and application of it in the next class. But I'm going to stop here, and I would be happy to answer any question you may have. So Rohit, to answer your question, if you have initial conditions that affects the behavior, so it's very important, that affects the behavior of the system. When the system is simply stable, if the system is asymptotically stable, or if you want system to be asymptotically stable, initial conditions will not change the solution, the steady state solution. So initial conditions dictate the transient solution, but the steady state solution is dependent on the eigenvalues, If you are designing a controller so that it stabilizes, then what that means is the initial effect of ill effect of initial conditions can be taken care of. They will compensate. I hope that answers your question. But again, I will show it to you with actual MATLAB simulations because words are only words. So, all right. That's it for today.